let me introduce to you Alberto Madonna from CSCS ETH.
Thank you, Brian. Good afternoon, everyone, from my side. I am Alberto from CSCS. I'm a software engineer there since quite a few years now. Understatement. Okay, so and for the last stretch of the conference, I would like to talk to you about a bit about Linux containers and what we can do with them with OCI hooks and a tool that we developed that it's called Sarus. So just give a quick overview of how I want to structure this presentation. I'm going to start with giving a little bit, establishing a little bit of a context about flexibility, the flexibility of containers in HPC, why we might want to give it some thought, give it some attention. I'm going to introduce OCI hooks and Sarus, explain what they are and how they're interesting. Then I'll move on with a showcase of OCI hooks with a live demo on Pitstein. Hopefully, if the HPC gods smile upon me, this will go smoothly. So, and I will show a few use cases, prominent use cases in HPC, MPI, workload manager integration, SSH integration. And then I will conclude the talk. So, containers and HPC. So if we take a look back, quick jump into the past, looking at about 7-8 years ago now, maybe even 8-9 years ago, at the very beginning of containers in HPC, the original use cases for the introduction of containers in HPC was to enable user-provided software stacks. So the users would have the capability to bring in their applications with all the dependencies and install whatever version they wanted with whatever dependency they wanted without going to asking politely, hopefully, to the HPC staff to install the specific software that they needed. So fast forward to today's, that use case is mostly there, but things change very rapidly. And scientific computing is evolving, and now we also have AI who's joining the party. So containers are being pretty much pressured to go beyond this original use case. Why? Because there are an increasing amount of third-party sources, for example, third-party portals, which provide images which users might want to use, and the software stacks are becoming more and more complex. The prime example would be the NVIDIA NGC with their AI and ML containers with these huge machine learning frameworks. So basically, it's getting increasingly difficult for any one person to completely own the stack and be able to produce a full image on their own. So we might have these images with different provenances. Containers might be expected to run in an increasing number of contexts and platforms. We might want to run containers on different HPC providers. Maybe we want to move them to the cloud. And then there is a growing complexity of use cases as well. It's not just I want to run my application, but maybe I want to interact with my application. I want to interact with my containerized environment. I want to debug it. Maybe my workflow is composed by different containers, which might be chained or interact between them in several ways. So lots of different complexity and rapidly growing complexity. So containers in HPC, I would say that they need to be flexible and extensible, because they need to run. We want them to run fast and efficiently on different infrastructures, and even on, and they might have to provide more features than they were built with. I'll make a few examples later on. So in both of these cases, one might argue that, well, just produce, once you have an established container, base container, just makes a different flavor. You want interactivity, just put an SSH software in it. You want to run on different fabrics, just put different MPIs or different underlying libraries. So create multiple versions of multiple flavors of your image. While this is a possible solution, it's probably not I would argue that it's not the ideal one. So I think we need to do more with containers instead of making more containers, at least. That's what I think. So where can we find these flexibility and extensibility that we want containers to have, ideally? Well, we might look at something like the Open Containers Initiative, or OCI. So the OCI, if you've never heard about it, it defines itself as an open governance structure for creating open industry standards around container formats and runtimes. So basically, it's an alliance of key players and leaders in the container space that has been existed since 2015, I believe. So Docker is there, Red Hat, Google, AWS, Microsoft, you name it, they are here, and they contribute to the standard formats and specifications that the OCI produces. So basically, Docker is OCI compliant, Kubernetes OCI compliant, and I can go on and on. So the most interesting aspect, or the most interesting detail in the context that I'm talking about, is that the OCI runtime specification defines an interface to plug in or hook external programs at certain points in the life cycle of the container. So here at the bottom of the slide, I have a graphical representation of the life cycle of a container from the creation to destruction. And basically what this specification says is that at specified points during the lifetime of a container, we can call upon arbitrary executables to take some actions. So for example, and these can be any kind of executable. They can be a binary, they can be a shell script, as it's represented here. And the most interesting thing is that these programs, these hooks, can customize the container autonomously, independently, and modularly. So more or less, how does it look? It looks something like this. We come in with our container image, with our layers. We run it through an OCI runtime. And before the container process is started, these hooks might come in and do stuff. We might have them create some files, do some bind mounts, so mount additional stuff from the host into the container. They might inspect the content of the container and take some other actions, or even start programs. So the team I've been working with at CSCS, and CSCS in general for that matter, we thought that this was a very, very interesting possibility, a very interesting capability that these standards give us. And we thought that it was, so much that we created our own container engine to run these hooks in HPC. And that's what we call Sarus. So Sarus is, as I said, is a container engine for HPC, as I just said, with compliant with OCI standards. And its main goal is to combine the portability of containers with the native performance of HPC. So that we might take our container image with CUDA and MPI or whatever your software stack is, and so we might have the system administrator configuring an OCI hook to inject optimized MPI libraries and network devices to be injected within the container. Or we might even leverage hooks developed and distributed by vendors like NVIDIA to add GPU devices within the container and get that so we can go from the image all the way to enjoy the benefits of HPC. More in general, Sarus is based on 4 core principles. First one is that we want to take advantage of the portability of images. We don't want to rebuild images for each system where we want to run. Second one is that in order to do so, we want to augment images with the missing resources that they need to tap into the hardware potential. We want portable images, but HPC containers. 3, we want to perform these augmentations not with mechanisms built into the engine itself, but we want to decouple specific features from the engine. And so in this sense, we also want to outsource the development to vendors and specialists. Number 4, these outsourcing, so these decoupling should happen through open interfaces, so that we can through standards, so that we can facilitate the development and reuse of these components throughout different container tooling, for example, and we can also facilitate involvements of new partners and vendors. CSCS has offered Sarus in production since 2019, and over the years we have made several benchmarks. Just to pick one of the most representative ones, we did in 2019, just to show that we have run Cosmo, a container of Cosmo, that would be the numerical weather prediction code used by several national weather forecasting institutions all over Europe. And we run it to up to 2,300 nodes of PITSDINT, just to demonstrate that we could scale containers. And I think we had a couple of runs where we also went almost to 4,000. And here we have a weak scalability test of a near global simulation with Cosmo, comparing native and containerized software. And the performance results are within 1% of each other, with basically the same numerical results. So this is an example of where we can get with OCI hooks to enhance containers and deploy and utilize them through Sarus. So if this is the what, which are the, let's say, the ingredients, the cogs the components that we can reuse to get to this result? Well, this is what I want to talk to you about next, to showcase individual hooks and about the most interesting use cases and how we can use them, and the interesting thing we can do with them. So the first one, which is arguably the most famous and popular one, or rather the one that people are most interested in, is the MPI hook that comes bundled with Sarus. So the MPI hook is this program that replaces the container MPI, so the MPI libraries, the MPI installation within a container, with a counterpart from the host. So there is a host library optimized for the fabric, for the network where we are running in on the physical host, that is replaced seamlessly in the host optimized library and MPI stack seamlessly replaces the one into the container, which might be generic. And so, since we now have an MPI optimized for a machine where we are running on, we are able to achieve native communication performance. In order to do this replacement seamlessly, the hook relies on ABI compatibility. So each and every library, whether it is the MPI or any of its dependencies, must match a counter. Rather, that's not correct. It's mainly on the MPI, but the MPI must match the ABI compatibility between the one on the container and the one in the host. This happens completely transparently to the user. In fact, Sarus offers just a convenient command line option, --MPI, to trigger the hook and to trigger this replacement. So this is very convenient for the users who doesn't need to know the intricacies of how the image is created, where stuff is located in the image, where stuff is located on the host. And we get the results like, here in the slide we have an all-to-all latency test between 1 and 128 nodes, and we basically, just to represent that we can get native results also with the container. So how does this look? This is where I jump in. This is where I jump into PitsDyn and hopefully try to show you exactly how does it feel to what is the difference and how do these things work. So for example, I want to run on 2 nodes. Oh, typo already, not a good start. And I want to run my container. I got the OZU micro benchmarks, version 7.3 with MPitch 343. 343, I said. Built on top of libfabric 1.18.0 with CUDA 11.8. And I want to run an OZU latency benchmark. So basically, this is a container that I built on my laptop without any specialization for PitsDyn. This is just on top of Ubuntu. So this is basically MPitch 343 as vanilla as you can have. Of course, the MPI has no idea about the optimized high-speed areas interconnect of PitsDyn, and so it ends up communicating through TCP sockets. Here on the right side, on the left side, you see the size of the messages, of the data packets being exchanged, and on the right column, there is the latency between the 2 nodes. So we have 2 containers on 2 different physical nodes exchanging data, reporting the latency. And as you can see, yeah, it's not that great. It's just finish it up. But now, since I have an MPitch-based containers, and the native vendor-provided Cray MPI is also based on MPitch, and these are ABI compatible, I can trigger the MPI hook to perform the replacement. Just a couple more seconds. And here it is. This is the native latency performance of the areas interconnect. So fairly easy to use. But what happens if I don't have an MPitch container and I have an open MPI container? Well, in this case, it won't work. Not this thing, and not out of the box, not this way, because OpenMPI is just not ABI compatible with MPitch. There are 2 different implementations. Even if we match the ABI strings, like I cannot put one on top of the other and hope that the application works. But maybe we don't need to work at the MPI level. We will need to look for something else. So, for example, this image is based on, it uses libfabric, and the MPI is compiled with libfabric, which is a communication framework. It's a middleware. It basically abstracts away the networking hardware from the MPI. So maybe we can do something there. But the MPI option itself looks kind of restricting because it's just sitting there. So we will need a way to pilot it to do something else. Maybe we will need something like an MPI type to say which type of containers we are actually dealing with. And in this case, I would like to work on at the libfabric level. So what happens if I try this? I just ran an OpenMPI container without any trace of the vendor-provided Cray MPI at near-native performance on an XC system. So what is happening here? Let's go in order. So the first thing to note is that There are different approaches with which we can achieve near-native performance with containers. The two that I've shown you are basically schematically represented in this slide. One is the full MPI replacement, or we can work to modify components of libfabric. Oh, okay. I don't want to go in the details because this is a completely different presentation. If you're interested, there is a paper about this that me and my colleague Thomas have worked on that goes into the rabbit hole of all these intricacies. But just the main point that I want to make is that there are different technological approaches that we can choose. And Sarus gives us a mechanism with which we can easily switch and select which one of these approaches to use. And this is implemented through these MPI type CLI option. So through the MPI type allows me to select and choose which one of the different hooks related to MPI the system administrator has configured on any given installation. So for example, I might want to slot into the container an mpitch compiled with a GNU compiler, or an mpitch compiled with a Cray compiler. Or maybe completely change approach and use a libfabric-based approach. And of course, the --MPI selects the one that selects the hook that has been identified as default one. Okay. So we might have multiple hooks, and we know we can choose about one of them. But how do we know which hooks are configured on any given Sarus installation? Well, we might ask nicely, right? The Sarus hooks command will list all the hooks that are currently configured and valid for a given Sarus installation. And it will print like the name of the hook, the path of the executable which will be picked up, and the stage where the hooks will execute. If I use the MPI option to the Sarus hooks command, then I will get a list of the MPI-related hooks that have been configured with the values that I might actually use to trigger a specific MPI type within the MPI type option. And it will also tell me which one is the default. Okay, okay. So I said there are different approaches. The MPI replacement, as I mentioned, is taken care of by the MPI hook. This is what the MPI hook will do. We'll take our host MPI and build it into the container. However, the MPI hook is very vertically developed to do this exact task. And so it cannot take care of, for example, the injection of, the injection of a libfabric provider. For that, we need a different hook. And we call this the mount hook. So the mount hook will just perform a sequence of arbitrary bind mounts of device mounts into the container. So it provides a convenient way of defining and performing a specific, feature-specific group of mounts. So for example, you know that you have a feature in your host system that in order to be available within a container just needs a series of libraries or directories or configuration files mounted within the container. Through the mount hook, you can expose this feature through a single switch to the user, or maybe even no switch at all, and have it always be active. The configuration of the mount hook uses the same syntax as the as the mount and device options that you might find in Sarus, Podman, or Docker. So if you know how to use Docker and Podman, the CLI, you pretty much know how to configure this hook. As example use cases of this hook, there is the one that I just showed you, the injection of a libfabric provider. We can mount Nickel plugins for for making nickel communicate through libfabric. The ones that among you dabbling in ML and AI might have heard of this thing, that we need nickel over libfabric. But we also can do more exotic stuff, like exposing the host Slurm within a container. How does it look like? Let's have a look. So let's say I have one I want to run a Ubuntu container. And this is the official image from Docker Hub. Plain old Ubuntu. Not old, but plain trusty Ubuntu. But I have configured one hook in this installation. And I can just add an annotation like this. Okay, I'm into a container. Let's see. I'm into a Ubuntu container. Okay, that's fine. But there is a run inside this container, inside this plain vanilla Ubuntu container. And I can see my job that I have allocated from the host system. And it is indeed the one that I'm running in, because this is step ID number 4. So, typo here. And I'm indeed inside Slurm step ID number 4. So from this container, I have access, I can attach to the, or attach, I can access the Slurm on the host. So what other things can we do, for example, if we have Slurm inside a container? And this is the most delicate part of the demo, because Slurm might not be that responsible in giving me this node. So maybe let's wait a little bit. Any questions up until now? Maybe I can take a question real quick. No?
So I have a question.
Yeah.
It's regarding the Slurm client. So you have the binary inside the container?
This is mounting Slurm executables, Slurm configuration,
Okay. So
and the Slurm socket,
yeah.
and any dependency.
So there's no Monge, no any additional stuff. It just inherit everything that you have from the host
Yeah,
and run.
exactly.
Okay.
There is a disclaimer to be done. There is an important disclaimer to be done. So SCEDMD does not recommend to expose containers, to expose Slurm within containers in this way. So they say that doing this is looking for trouble. But I'm just saying, it's a possibility if you want. So, for example, now that I got a node, I can see that I'm still inside my Ubuntu container, but now I have access to a different node. I can see that through Slurm, I can go to the native, operating system of that node, because this is the SUSE-based Cray operating system. So I can also do some stuff like that. Come on. Okay. So I can run a Fedora container from a Ubuntu container through Slurm on a Cray XC system, which is not something that maybe you see every day. So I think this is interesting. Admittedly, it's true. If you have a workflow engine to chain together different containers and orchestrate different containers, the workflow engine will probably take care of something like this for you. But if you don't have access to a workflow engine, or maybe you think your use case is not complex enough to warrant the use of one, this is a possibility.
So I have another question. And since I can see that you have your username is used inside the container. So by default, Docker and any container engine just will be using root, give access. So how that is getting mapped here to be able?
This is done by Sarus. This is done by Sarus, which, like every other HPC-focused container tool, like Singularity, Charlie Cloud, and the other ones, they will always remap you to your actual user. Like to the user you have on the host, they will drop you into a container with the same user.
In this case, if you generate any data here and you are writing to the file system, then that will be just inherit your UID and GID and all these details.
Yeah.
Okay.
Yeah.
Okay.
Yeah. There are ways to do this user, like to drop you into the user you were on host, also in the container, to have the same user also on other generic container tools like Docker and Podman. But this kind of, it's not user mapping, but having the same user, it's basically a default feature of HPC container runtimes. Okay, so I can just relinquish both my allocations. The last hook that I want to talk about, I'm running low on time. The last hook that I want to talk to you about is what we call the SSH hook. So this is a program that will mount a standalone lightweight SSH software, we currently use Dropbear for this, into the container. It will automate the startup of the SSH daemon, and the hook will also do its best, will try very hard, to provide an experience when you connect to this SSH client, to provide an experience that is as consistent as with regular container shells as possible. This is convenient when you want to connect to containers, but the container image doesn't include an SSH software on its own. So the hook is also able to generate its own set of keys, and will use these keys when connecting between containers. And the hook also can authorize public OpenSSH keys for remote access. So that you can do something like things like this. So let's say that I have a Python file. Let's say that I have this Python script, and I want to run it and debug it from my laptop, from a Visual Studio on my laptop. I will not type the command the command continuously, because this is quite complex, but I will just comment on it. So I will start a container using the PyTorch image from NGC. So this is an NGC container with a full PyTorch framework inside it. Just to say, this is an image that can come from a third-party repository. It doesn't have connectivity tools and whatnot. And I will open a bash inside it. I am mounting Scratch inside the container, because that's where the Python script is. I'm activating the SSH hook, and through this annotation, I'm asking the hook to also authorize connections from this public key file that I have uploaded to PitsDyn beforehand, and is the public portion of the SSH key that I normally use on this laptop. So let's start this container. Okay. So yeah, I'm inside the PyTorch container, and I need to take note of the host name where I am, the IP, so I can go to Visual Studio on this other workspace, can slot in the IP on my SSH configuration, save it, okay. And then I then I can launch the remote connection extension of Visual Studio. The client is transferred, and the server is set up. And I am connected to my container on PitsDyn, to my NGC container on PitsDyn. I can control it through the terminal of Visual Studio. You can see that the same file is here. I could work through the terminal, but I can also do more. No, before I do that, I'm going to the extensions, because I need to set up the Visual Studio server in the container. So I will install the Python extension and Python debugger extensions for Visual Studio. Okay, these are done. So now I can, for example, I can open a folder, and I want to open Scratch. Notice that the drop-down menu is reflecting exactly the directories that I have on PitsDyn. Where is this? HPCAC, there you are. Here's my file that I have just opened, and I can just set up a breakpoint, run and debug the Python, and run it with the Python file. There, I've hit a breakpoint, and I'm debugging from my laptop, from Visual Studio in my laptop, a Python file that is being hosted on the compute node of PitsDyn remotely. I can step over the code. We can see here that the local variable views are getting populated. I can step into functions. I can see the live thing. Whenever something is printed, I see it on the terminal. I can just complete the execution. So yeah, I could potentially do this with any Python file. This is rather a trivial example, but I have colleagues that are using these to develop and debug PyTorch networks and other ML use cases. So, but if at some point, and I can also do another thing, for example, if I cannot just debug, I can write code, and I can edit the thing. So if I don't like the 5 anymore, let's say that I want to make the variable a that is 7, I just change it, I save it. If I get back to my container, you see that the file has changed. So I was actually editing the file remotely from my laptop. And when I'm done, I can just disconnect from Visual Studio, and then I close the container. Yeah, okay. So, in conclusion, OCI hooks are able to modularly extend containers and OCI runtimes for functionality or performance. We can do things better, or we can do more things. And the OCI hooks are the, let's say, the secret sauce that help us connect container portability with the portability with the infrastructure-specific nature of HPC, because we have very specialized hardware. Sarus enables us to run and to apply OCI hooks to HPC use cases and to use them very conveniently in HPC. And the software already comes bundles hooks for prominent use cases in HPC, as I've shown today, MPI, bind mount-based features, libfabric support, Slurm, and SSH. All of the code, all of the software that I've shown today is open sourced on GitHub under a BSD 3 closed license, if I remember correctly. We have a full documentation on read the docs about the Sarus engines itself, and about the configuration of OCI hooks. How do they work? How can they be set up? And since they are OCI hooks. They are not just tied to work within Sarus. You can use them potentially with any OCI compliant tool. If you're looking for a more formal introduction to the presentation of these topics, we also published a paper a few years back. And yeah, that's pretty much everything from me. Thank you very much.